Okay, in this video we're going to continue with sorting algorithms in Python 3, and we've already created a sorting template, and if you see here, I've duplicated this template, and now we're going to modify this mySort function. This mySort is basically now going to be our insertion sort. Last time we did a bubble sort, and this time we're going to do an insertion sort. So what is insertion sort? Okay. If you go to geeksforgeeks.org/insertion sort, there's a good example of an insertion sort. So say we have this set of numbers, this list of numbers. What happens is to the left we keep a maintained sorted list. All right. So initially we'll start with the second item in the list because this first item by itself is automatically sorted. So think of this as partitioning your list into two sublists. One sublist to the left is always sorted. Okay, so we start out with this sorted sublist, and then we take the next item, and what we do is we need to insert it into this sorted sublist. Okay, so to insert it, we go one item at a time, comparing these two elements to see where it fits. Now this doesn't, it makes more sense once you go farther down here. So for example, if this is our sorted sublist and I have the number 1, we're now going to go through each one of these elements and compare 1 to the number there to find out where this element 1 is supposed to go. Does it go here? No. We have to compare it to here. Does it go there? No. Does it go here? No. Does it go here? No. Does it go here? Yes. And so then we insert 1 and all of the other items push forward. So in reality, what we're doing is we're just swapping here. So the 1 and the 12 swap. And so 1's here, and we look at 1 and 10. Do they need to swap? Yes. We look at 1 and 4. Do they need to swap? Yes. Right? So that's basically what we're doing. So the first time through, when we have a brand new list, our sorted sublist is just that first element, because one item in a list is by definition sorted. There's nothing out of order. Okay, so then we would take this number 3. So on the second line here, the number 3 has to be compared against all the elements in the sorted sublist. Well, not all of them. It just has to be compared until it's in the right order, and then it stops. So we compare 3 and 4. Are those in the right order? No, so we swap them. And there's no other items in the list. So now our sorted sublist is 3 and 4, so that you see that in red here. So the new item is the number 2. So we have to look and compare the number 2 to each one of these items until we find where it goes. We do that by comparing 2 and 4. Is that in the right order? No. So we swap. 2 and 3. Is that in the right order? No. So we swap. So the right order ends up being 2, 3, 4. Now we have this item 10. So we're going to insert 10 into our sorted sublist here of 2, 3, and 4. So right away, we compare 10 and 4, and are they in the right order? Yes. Since this is all sorted already, if 10 is greater than 4, then by definition it's greater than the other elements as well. So it just stays where it is, and this list here becomes the sorted sublist. Okay, so 2, 3, 4, 10 is sorted. That's our sorted sublist. And we're going to try to insert 12. So we compare 12 to 10. Is that in the right order? And yes, they are. So now this is our sorted sublist. So now we've got an interesting one. We're going to try to add 1. Okay, so this is our sorted sublist, 2, 3, 4, 10, 12. So we have to compare 1 with 12. Is that in the right order? No. So then we compare 1 with, then we swap them, right? So 1 is now here and 12 is over here. 1 compared with 10, is that the right order? No. So swap. So 1's here now. 1 and 4, no. Swap. 1 and 3, no. Swap. 1 and 2, no. Swap. And then 1 ends up back here. So we see 1, 2, 3, 4, 10, 12. Okay. So you see, each time through the loop, we don't necessarily have to go through all of the items in the sorted list. We just have to swap until we find where this element goes. Okay, so here's a good example, the number 5. This is our sorted sublist, right? 1, 2, 3, 4, 10, 12. You can see those items are in the correct order. And I want to insert 5 into that sorted sublist. So I compare 5 and 12. Is that the right order? No. So we swap. I compare 5 and 10. Is that the right order? No. So we swap. 5 and 4? Yes, that's the right order. So the 5 stays here. So we end up with 1, 2, 3, 4, 5, 10, and 12. And the same thing happens with 6. Try to insert it, and then when you finish, you have a sorted list. Okay, so this is the idea behind insertion sort. You have a list at the beginning that consists of just the first element in the list, and that is your sorted sublist. Okay, and then each item from the remainder of the items in the list, you're going to try to insert into that sorted sublist. And to do that, you just compare, and if they're out of order, you swap. And if they were out of order, you have to compare again and keep doing that. So in the worst case scenario, you will go from the position of this item and you will have to compare all the way down until, in this case, 1 has to make it all the way down here. In other cases, though, the list could just be in order already. So here we tried to add 12 to this sorted sublist, and it was already in order, so we didn't have to make all of these comparisons. Okay, so that's the concept behind insertion sort. So let's take a look and see if we can code up insertion sort with Python 3. All right, so we've already created our swap function, so we can use swap whenever we want. And we've got sorted, so we made a duplicate list. We duplicated the list of unsorted numbers, and so sorted is our list, and that's the list we're going to modify to create some sort of sorted list. All right, so our algorithm goes here. So we're going to start with some loop, right? So we can make a for loop for I in range, right? And we'll leave the range blank for now. And that outer loop is going to be basically how many times do we have to try to insert one of these into the sublist, right? So if the first item is the first sorted sublist, that means we're going to have to try to insert 3, and then we'll try to insert 2, then 10, then 12, right? So it's the length of the list minus 1, because that 1 is the first sorted sublist. So each of these items we're going to have to try to eventually insert into the sorted sublist. So that's 1, 2, 3, 4, 5, 6, 7 items in a list of 8. Okay, so that first for loop then looks like it's going to be, we'll go from 1 to 9. Or we could go to, it wouldn't be 9, it would be the length of the list. Or we could just go to length of sorted. Okay, so this is the same as saying we're going from 0 all the way up to the length of sorted, which would be 7. All right, we actually want 1 less than that, so minus 1. So this loop is going to run 1 less times than the number of elements in the list. Okay, and that's because for each one of those, we're going to add one of these into the sublist. All right. So we need a for loop here now. This for loop is going to be a little bit different. This for loop basically is going to be the number of times we compare. So, for example, if 4 is the sorted sublist to start with, and I'm inserting 3 inside the nested for loop, the second for loop, I'm just going to have this one comparison, and then I'm done. The maximum number of comparisons I can have is this one. So if I'm adding this item, the maximum number of comparisons I can have is a compare here, and then another compare here. I might not need all of them, but that's the maximum. So when I'm adding another item here, I would compare here, here, and here. So there's a pattern. We're increasing the number of times we iterate through that inner loop. So the first time it's once, second time it's twice, third time it's 3 times, and then 4 times, and it keeps going and going until eventually we get all the way up to 1, 2, 3, 4, 5, 6, 7 compares, right? In this list has 8 items. Okay, so 7 compares is length minus 1. So again, we're going to have something to the effect of for I, or for j, we're going to use a different variable. We don't want to use the same variable. J in range length of our sorted list minus 1. Okay, so this is what the inner loop is going to be at the very last insertion, right? But the very first insertion, oops, let me go back here. The very first insertion is just going to be 1 item. So what we want to do basically is this for loop is going to change. Okay, so every time, it's not going to run the same number of times each time. So right now, if we had a list of size 8, like this example, that means this for loop would run 7 times, and then this for loop each time would run 7 times, and that's 49. 7 times 7. But what we want is we want this for loop the first time to run once, second time it should run twice, third time it should run 3 times. Right? So how can we do that? Well, this I value is increasing every single time this loop runs. Okay, so the first time this loop runs, we could have this loop have it start out at I and then go down to 0 by decreasing each time. Okay, so this first time through I is 0, so this wouldn't run at all. We actually want I plus 1. Okay, so this will give us the first time through this loop I is 0, right? So then this inner loop is going to create a list of numbers. 0 plus 1 is 1. We're going to go from 1 to 0 by -1. So this is going to create a list starting with the number 1, and in the range function, your end term is never included. Okay, so this is just a list of 1 item with the number 1 in it. All right, so let's just print this out before we go too much further to see what we're working with. So this is what you're going to have to do commonly on these sorting functions. Print out your I's and your J's and your K's and whatever to make sure you understand what's happening. So in this for loop, this I is going from 0 to the length of the list, and we're going to give it a list of 8 numbers to start with. All right, so let's test this out. Go to desktop, CD, desktop, and then Python 3, insertion sort, and we're going to give it 8 numbers. So what are the 8 numbers? 4, 3, 2, 10, 12. 4, 3, 2, 10, 12. And 1, 5, and 6. 1, 5, and 6. Okay, so we haven't actually sorted anything yet. We're just returning that list as it is, so the sort should fail, but what we're looking at is this for loop. We want to see I and J get printed out and see what those values are to help us understand. Okay, so I is 0 and J is 1. Then I is 1 and J is 2. I is 1, J is 1. 2, 2, 2 for the I, and it goes 3, 2, 1. Right, so this looks about right. We have the first time through the loop I is 0, and that inner loop should only run 1 time. Right? And it does. That I value is 1. Second time through the loop I is 1, and the inner loop should run twice, and it does. We have 2 items here. Third time through the loop I is 2, and so the inner loop should run 3 times. Right? So this appears to be working, and each time through the list, our J value here corresponds with the item, the index of the item that we might want to be swapping. Okay, so if we look at this in context, I is 0 and then j is 1. So 1 is the index of the item we're inserting. Right? So this is index 0. 1 is the index of the item we're inserting. And we need to compare and possibly swap. Right? Here, 1, 2 is the index of the item we're possibly comparing. We need to compare these two items, 2, right? 2 and the 4, and possibly swap. Then we see on the inner loop we're at index 1, and we need to compare that with one less than that index. Okay, so whatever our j value is here, we're going to have a k value that is 1 less than that. K equals j minus 1. Okay, our j value, as we saw, let's go back here. The j value, as you saw, is the item that we're adding, and we're going to compare that with the item that is 1 index less. Okay, and then swap if necessary. Then we'll be comparing, so like when we're inserting this number here, we're going to compare this index is j, k is going to be j minus 1, so that's going to be this index. We're going to compare those two elements, swap if necessary, and then iterate through the loop. And then j will be 1 less than it was, k will now be 1 less than j, and we compare those two items. Okay, so you might have to go kind of slow and print out all of the results from the for loop to try to understand exactly what's happening here. Alright, so let's get rid of this print statement. So j and k are the indices of the elements that we would like to compare. Alright, so if the item in our sorted list at, let's see, it would be j, if that item is less than the item in our sorted list at k, so remember k is the index before j, j is the index of these green items, j is initially the index of the item we are inserting, and k is always 1 less than that, so we're comparing those two items. So if the item j is smaller than the item k, that means we need to swap. So we swap by passing in the sorted list, and we pass in j and k. And it doesn't matter which order you do that. You could do k and j for the swap. It doesn't matter because they just swap. Okay. Now we could go ahead and finish through this for loop. So for example here we would compare j would be index, so 0, 1, 2, 3, 4, 5, 6. This is index 6. J would be index 6, k would be index 5. We would compare those items. Do they need to swap? Yes, 5 needs to come over here and 12 goes there. So now we're the second iteration of the for loop, and j is 1 less than it was, so that is 5 now, and k is 4. We compare these two items. Do they need to swap? And this is a 5 now. Do they need to swap? Yes. And it finishes out here. Now I could keep comparing. I could keep comparing and say, is 5 smaller than 4? No. Is 5 smaller than 3? No. I could keep comparing, and it would still sort the list, but I know at this point I no longer need to keep comparing. It's just a waste of cycles. For only 4 items, it's not that big of a deal, but let's say I had 4,000 numbers back here. I wouldn't need to go through that loop 4,000 times, or 4 million even. Okay? So really, if I want to be efficient, I want to stop iterating through that inner loop right here as soon as I found my spot. So how do I know when I found my spot? Well, if I haven't found my spot, I have to swap. If I have, then the sorted number, the item at index j is not less than the item at index k. Okay, so if j is less than, that means they need to swap. Otherwise, that means I'm done. So I can use the special Python keyword break, and it will break out of the closest loop in scope. Okay, it won't break out of the big loop. This is going to break out of the closest loop in scope. All right. So let's go ahead and add our work in real quick. So for comparisons, work plus equals 1. That's our comparison work. And then swapping work. Work plus equals 1. Okay. Now again, we're rather arbitrarily assigning work values here. Swapping might actually be more like 3. It's supposed to mimic computer cycles, CPU cycles, right? So realistically, swapping an item is going to be several CPU cycles. Comparisons might be 1 or 2, right? But swapping will be more. But it doesn't really matter. We're just trying to quantify this a little bit so we can look at how many units of work it might take for an algorithm. All right. So we're being a little bit unscientific about that, but that's fine for demonstration purposes. Okay, so this is the swapping work, and when we get finished, we'll return the sorted list and the amount of work. Okay, so if we take a look here, clear, and run this again, we see that our sort succeeded. Okay, so the sorted numbers ended up the same, and we had 28 units of work to sort. All right, now this is, let's take a look at this without this break. Okay, we had 28 units of work. If we do this again, the sort still succeeded, but you see we had 40 units of work. That's because we kept having to do this comparison, even though logically the way we designed this algorithm, this code should never need to be executed, but the program does what it tells it, what we tell it to do, right? We told Python to do this, so it does it, even though there's no possible way we need to, right? So this is how you can make algorithms efficient. You have to be careful, and you have to consider exactly how they're going to be executing the code, and is there a reason to continue doing comparisons, right? In this particular case, we designed this algorithm such that everything before the element to be inserted is a sorted list. So once you find the location for this element, you don't need to compare any farther because everything below that is going to be less than that element, right? So that's just an artifact of the nature of this particular algorithm. You know that you can stop once you reach that certain point, once you reach that insertion location. Okay? So this is insertion sort. And there's a couple of other ways you could do it, but this is pretty much the idea. And if you go down here, we need to modify this for each algorithm. What is our time complexity? So we can take a look at this, and we can see again that we have 2 for loops that are based on, well, the first one is based on n, which is the length of our list, and then j isn't based on the length of the list, but it is based on I, which is based on the length of the list. So this one too winds up being n squared. And you can analyze this a little bit more, but remember the constant terms drop out and only the dominant term applies. Okay, so when you have something like n squared plus n plus 2, the dominant term is the n squared. That's the most important term. The other terms don't even matter. Okay? If I have 5 times n squared times 32 times n or plus 32 times n minus 14, right? We can, the largest term is the n squared term, and we can get rid of any constant factors of that number. Okay, so just n squared is good enough in terms of big O. So the time complexity for this one is big O of n squared. All right, we'll run it one more time so we can see that output. Clear. All right, time complexity of the sort is big O of n squared. And then we can try a bunch of bigger numbers. I'm going to try a few more. Run that, and sure enough, sort succeeded. So we are comparing this to the Python sort. So that's, as long as that is working appropriately, which our assumption is it is, we can also like verify by manually going through each of these numbers. It looks like I had the number 1 twice, but that's okay. 1, 2, 3, 4, 5, 6, and we can see these are always increasing. As long as they're always increasing, that means we sorted the numbers correctly. So that is insertion sort.